All right, so take it away, Ashwin.
Oh, hi, can you see my screen and hear me?
Yes.
Oh, thank you. Hi, I'm Aswin, PhD student at the University of Sussex, working on the flare simulation that Chris just introduced. I would like to thank the organizers for giving me this opportunity to talk about my work. And I'll go on and talk about the photometric properties of galaxies in the flare simulation. As Chris has already given us a comprehensive introduction to the flare simulation, I'll skip some of the pleasantries of the flare work and move on directly to reiterate another point, which is about the effective volume we are probing with this big box that is available to us. So this effective volume gives us access to the large-scale power available in the 3.2 co-moving gigaparsec volume at the Eagle reference resolution. With the use of our weighting scheme, this allows us to extend the dynamic range at the bright end. So this is really complementing the upcoming new generation telescopes like Euclid, the James Webb, and the Roman Space Telescope. So with this effective volume and the large number of galaxies that were shown by Chris, we'll now show some of the photometric properties of the galaxies that are generated in the simulation. So I'll briefly introduce here how the photometry of the galaxies are being generated. So for modeling the photometric properties, we adopt a simple line of sight dust extinction model. So I show here a cartoon representation of the method. Uh, we use BPAS to generate spectra for each star particle in the simulation, treating them as a simple stellar population. We trace this along the line of sight, which is the z-axis in our case. The starlight is attenuated by their birth cloud component as well as the intervening interstellar medium. Now we assume that this dust content is proportional to the metallicity of these components. There have been a few studies which have shown that there is a gradual evolution in the metallicity, but we ignore this for this work and will try to probe that in a future work. Now these two are the free parameters that are introduced in our model, which is the attenuation introduced by the ISM and the birth cloud. Now we calibrate these two values so that we retrieve the Z equal to 5 UV luminosity function from Pavens et al. 2015. The birth cloud component is fixed by a simple visual inspection of some of the properties like the UV continuum observation at Z5 and the line equivalent with measurement Z equal to 8 from DeBarros et al., which shows the O3 doublet. Now, these are generated using this publicly available SynthOps module. The link for that is given below. You can go around and play with it and see what all properties of galaxies you can retrieve. Now with this modeling, I'll show some of the photometric results that are generated from the flares galaxies. So first we have the UV luminosity function. Here I show the UV luminosity function of the flares galaxies from Z equal to 5 to Z equal to 10, which are the colored circular data points in the figure. Plotted alongside is some of the observational results as well as some of the modeling studies. As you can see, we do provide an excellent match to the observations at all redshifts above Z greater than or equal to 5. One thing to note is that we do predict slightly lower number densities of bright galaxies that are predicted from the Schechter fits of some of the some modeling studies like Mason et al. 2015 and March 2019, the fire simulations. And these can be seen at redshifts above Z8 and Z9. So there could be an argument for the fact that we might still not be probing some of these brightest galaxies in the universe, but these are Schechter fits from their modeling, and it should be taken with a grain of salt. So we also try to provide functional fits to these data points, and we try a Schechter form as well as a double power law form, and we see that the Schechter form is a better fit to redshift 6, 7, and 8, while the double power law is a better fit to the other values. This was inferred using the Bayesian information criterion. So there is another instance where we see that there might be some brighter galaxies that we still need to probe to actually look at what functional form these galaxies do actually follow. This is something that we are interested in doing later. Now we look at the UV continuum slopes of the galaxies that are in flares. We can see that it provides quite a good match to the observed values, but the observations are you could say that it's kind of all over the place. So it's hard to constrain if these are actually providing the right values or not, but we do provide a good fit to these observations. We also see that uh, the flares galaxies have a flattening of the UV continuum values at the brighter end. This is something that I've been seen in other works of a flattening, not a clear flattening, but like the UV continuum slopes are much flatter than some of these observations show. But this is what the flares galaxies are showing. We also look at the attenuation in the far UV of the flares galaxies. What we can see is the attenuation is increasing with increasing intrinsic luminosity, which is expected. One thing you can see is some of the brighter galaxies that are in some of the intrinsically bright galaxies in flares are in the most attenuated. We also see that some of the galaxies have already moved on to the passive regime by z equal to 5. This might be much clearer if you plot it as a function of stellar mass, where you see more of these galaxies popping up. This is something we are studying at the moment. And we also show the environmental dependence of the luminosity function. So here I plotted the UV luminosity function as a function of the overdensity of different regions. And as you can see, the normalization is higher for higher overdensity, which is expected. We also see that the highest overdensities tends to follow a Schechter form with a hint of a double power law features at some of the intermediate overdensities. And in black, you have the composite function, which is being probed by some of the mean density regions. So it is a really good match to mean density volumes, our composite function. We also see no environmental dependence on the attenuation in the far UV. So here is the attenuation as a function of different overdensities, and we see the same behavior for the dust attenuated far UV luminosity. Now I compare some of the observations of the equivalent width measurements that we have from the flares galaxies compared to the observations. So here I show some of the observational measurements from Ryan Inslee and DeBarros 2019. We do predict, we do provide a good match to these observations, but as you can see, we fail to account for some of these high equivalent width galaxies. This could be because we don't model the effect of AGN luminosity into the effect of AGN into the luminosities that we are generating. So this is something that something that could explain some of these lack of high equivalent width galaxies. So this is something that we are looking into with one of Steve's students. And we also look at the C3 doublet here. Since we don't have much observations of that, I plot the flares Z7 equivalent width functions with respect to some of the observations that are available to us. So here also we have some of these high luminous objects having a higher equivalent width than we have predicted. So it is worth looking into the effect of AGN on these galaxies. So with that, I stop, and here are some of the future work that we plan on doing with these galaxies. So some of the bias, looking at the bias and cosmic variance, the size of galaxies, the morphology, and passive galaxies, as mentioned before. And we also plan on looking into the far infrared regime of these galaxies. So looking at some the potential impact for ALMA observations. And we do plan on making a higher resolution simulation to probe the faint, and any ideas and collaborations are welcome. Thank you.
Thank you, Ashwin. So we have some questions for you. We'll start with one from Casey Papovich, who asks, at the bright end of the UV luminosity function, do you have a sense of what in the models is driving the exponential cutoff? Why does it look more like a Schechter function than a power law? What physical effects are happening?
So it could be an impact of what is happening with the effect of the star formation rate in these galaxies as a function of the feedback that is happening at these ends. So we haven't actually looked into what effects these have, but yeah, this is something that we need to probe.
Okay, and then another question about dust from Maxine Trivich, who asks, do you have any sense of how the assumptions you make on the dust distribution affect the photometric properties of your galaxies?
Oh, yeah, that is quite a great question. So, so the dust would definitely affect any property that we measure from here, obviously. But so the grain size distribution and the attenuation curve that we actually choose to observe these galaxies would affect what outputs we see. So we did try some other extinction curves from literature, and what we saw was to get back some of these observational results, we do need something like an SMC curve to get back these properties, like the UV continuum slope. And an evolving dust to metal ratio would also make sense, since this is something that has been seen in observations as well as some modeling results. So yeah, these are all something that we definitely need to try and would love to do.
Oh, sorry, I was muted while I was asking you. One last question from Nathan Adams, who asked, do the simulations give any constraints on the AGN UV luminosity function in your lower redshift bin?
So we haven't actually looked at modeling the AGN luminosity function. So it's a work in progress, and we might be able to tell you soon about it.
One more question from Tom Thunes, who asked, what is the faint end slope of the UV luminosity function, and how faint below HST limits do you simulate?
Sorry, could you repeat that again?
They're curious about what the faint end slope is of the UV luminosity function.
Okay, so I do have some of the faint end slope that we tried to look at, and it is quite similar to some of the observational results. So here's a plot that I made of the UV luminosity function. It's the darker points would be the Schechter, and the light gray would be the double power law. So does that answer the question?
Yes, I think so. All right, so I think we should move on, but thank you, Ashwin.
Oh, thank you.